Hello students, today we are going to discuss limit, continuity and differentiability. So, what is limit of a function? Suppose y is equal to fx is a function. Let us represent it graphically. Suppose this is a function y is equal to fx. We want to see the behavior of function in the neighborhood of say x is equal to a. This is the x-axis, this is y-axis. So we want to see the behavior of this function, that is how y changes with x as x approaches to a. Okay, so x can approach to a from two sides. One from this side, which is from right hand side. This is called RH side, right hand side, and one from this side, which is called LH side, left hand side, right? So this is a point which is say closest to a from right hand side. So say let us name this point a plus, and let us name this point as this is point a. This is let me denote this point by another color. This is say point a, and these two circles are a plus and a minus. So we want to see the behavior of function y is equal to fx at limiting points, that is x is equal to a plus and x is equal to a minus. So we call it as limit of a function, right? So limit fx as x tends to a plus. What is its value? Its value is say f a plus, right? This value, this value, this value. This is just at x is equal to a plus, okay? And limit at x tends to a minus fx, we call it f a minus, a minus. Okay? So this is also known as RHL, right hand limit, and this is known as LHL, left hand limit. So if a function at x is equal to a plus and at x is equal to a minus have same value, that is if RHL is equal to LHL, we call limit of a function, that is y is equal to fx, is defined at x is equal to a. That means we have a unique value of f a plus and f a minus. So, and these two limits are equal to f is equal to a. Okay, so if right hand limit is equal to left hand limit is equal to f a, then limit fx as x tends to a, we call it f a, is defined. Okay, and say if this is not the case, okay, that is if the above case is not satisfied, then we call limit of a function at x is equal to a, that is limit x tends to a for fx does not exist or is not defined. Does not exist. Okay, so this is the concept of limit of a function. Now we have some formula for limit of a function. Say for some basic functions. Let us write for some basic functions. Let me give some examples. Say example. Suppose we have a function fx is equal to 1 upon x square minus 2. Okay, and let us find limit when x tends to 3. Okay, fx. We see, if we check this function fx, we see that 1 upon x square minus 2 can be written as x minus 2 into x plus 2, right? Let me change the function. Let me write the function x square minus 2, 1 upon x square minus 2 as, say, this is given. This is our given function fx. So fx is equal to x minus 2 upon x square minus 2, which can be written as x minus 2 upon x minus 2 plus x plus 2, right? So if you check the behavior of this function, at any point x not equal to 2, okay, when x not equal to 2, we can write this as x plus 2, right? If x is not equal to 2, then both above and below value, that is x minus 2 and x minus 2, we can cancel it and we can write it as 1 upon x plus 2. Fx is equal to 1 upon x plus 2, right? See, suppose we are calculating the value of f3. So what is the value of f3? That is 3 minus 2 upon 3 minus 2 into 3 plus 2, which is equal to 1 upon 3 plus 2, which is equal to 1 upon 5. But notice that at point x is equal to 2, what happens? Suppose we are going to calculate f2, then 2 minus 2 into 2 plus 2. This is 0 upon 0 into 4. We cannot write it as 1 upon 4, right? Because this is not defined at f is equal to 2, x is equal to 2. So f2 is not defined here, right? But if we see the limit of a function at x is equal to 2, that is, if we see what is the value of f2 plus, it should be 1 upon 2 plus 2, that is 1 upon 4, isn't it? Because at x is equal to 2 plus, the value 2 plus minus 2 is not 0. This 2 plus minus 2 is not 0. So here f2 plus and f2 minus is equal to both 1 upon 4. So the limit of a function exists and we can write limit x tends to 2 fx, where fx is equal to x minus 2 upon x square minus 4 as 1 upon 2 plus 2, which is equal to 1 upon 4. Okay, so this is the main concept behind limit. Where the function does not exist, we define its limiting value beyond or the point just in the left hand side or the point in the just right hand side. Okay, so let us define some basic formula of limit, some basic. Limit x tends to 0, 1 plus x to the power 1 upon x is equal to e. E is the epsilon, we call it exponential number. Then we have limit e to the power x minus 1 upon x as x tends to 0 is equal to 1. See, at x is equal to 0, these all are not defined. The functions fx are not defined, right? So we have first what type of values are indefinite, that is we cannot define it. 0 by 0 not defined. Then infinity by infinity is also not defined. 1 to the power 0 is also not defined. 1 to the power 0 we can write it as 1 to the power 1 minus 1, which is 1 to the power is defined. I mean 0 to the power 0 is not defined, which is equal to 0 to the power 1 minus 1, or we can write it as 0 by 0. So this is same as 0 by 0 form. Then again these basically we follow 0 by 0 or infinity by infinity. These are basically the same form. And one more form, which is 1 to the power infinity. This is also not defined. Why? because if we take a number which is just greater than 1 plus infinity is equal to infinity, and if we take a number which is just less than 1, that is 1 minus infinity is equal to 0. So at 1 to the power infinity is 1 exactly, but 1 plus something to the power infinity is infinity, and 1 minus infinity to the power infinity will be 0. So if something is tending to 1, something is tending to 1 to the power infinity, we cannot say that whether it is 0 or it is infinity. So it is also undetermined. So these are all undetermined forms. Okay. So we determine it by what the value of the function is tending to the given point, right? So this formula will help us to evaluate the limit. So let us recall all the formulas. Now the next formula is limit x tends to 0, 1 plus x to the power n minus 1 upon x tends to n. Then limit x tends to 0, ln log base e, that is 1 plus x upon x is equal to 1. Then we have some trigonometrical limits, that is limit x tends to 0, sin x upon x is equal to 1. We have limit x tends to 0, tan x upon x is equal to 1. Okay. We have limit x tends to 0, x to the power m minus a to the power m upon x to the power n minus a to the power n, where x tends to, in this case here x tends to a. So this limit is equal to m upon n a to the power m minus n. Okay. So these are some basic formula which we are going to use while evaluating the limit of a function. Also we have some expansions which are also useful while evaluating the limit. So we have expansion of e to the power x is 1 plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3 factorial plus dot dot dot. Similarly, we have expansion for sin x is equal to x minus x cube upon 3 factorial plus x to the power 5 upon 5 factorial minus x to the power 7 upon 7 factorial plus dot dot dot. We have the expansion of cos x as 1 minus x square upon 2 factorial plus x to the power 4 upon 4 factorial minus x to the power 6 upon 6 factorial plus dot dot dot. We have the expansion of tan x as 1 plus x plus x cube upon 3 plus 2x to the power 5 upon 15 plus dot dot dot. We have the expansion for 1 plus x to the power n, 1 plus nx plus n into n minus 1 upon 2 factorial x square plus n into n minus 1 into n minus 2 upon 3 factorial into x cube plus dot dot dot. So if we remember this up to this expansion, this is fine. Okay. So now this is all about the limit of a function. Now we are going to see what is continuity. How continuity is defined. Suppose a function y is equal to fx is said to be continuous at point A. This is a function y is equal to fx. A function is said to be continuous at point A when its limit exists at point A, right? So a function is said to be continuous at x is equal to a if limit x tends to a fx exists. Okay, that is limit x tends to a plus fx should be equal to limit x tends to a minus fx is equal to fa. Then function fx is said to be continuous. Okay, and if a function is discontinuous, then its graph must be discontinuous, somewhat like this. Say this is a discontinuous function where at x is equal to a, its limit is not defined. That is, when the function is greater than a, that is at a plus, its value is something which is different from the value at a minus, right? So this is the value at a minus and this is the value at a plus. Both values are different, so we call function is discontinuous. Okay. Now differentiability. Suppose we have a function y is equal to fx. We want to find the slope of a tangent at say point x is equal to a. We can draw a tangent at point x is equal to a, right? If there exists a unique tangent, if there exists a unique tangent at x is equal to a, then fx is said to be differentiable at x is equal to a, right? So a function is differentiable at x is equal to a when we have unique tangent at that point, right? So a function which is something like this is not differentiable at this point. Why? Because at this point we have this as a tangent, or we can have this as a tangent, or we can have this as a tangent. So we have infinite tangent at point where the function is being like a corner. So a smooth function is always differentiable. So what is a smooth function? Which is differentiable in all its domain. So at this point the function is not smooth. So we call function is not differentiable at that point because unique tangent does not exist. So how to check the differentiability of a function? So let us find the slope of a tangent. If the slope is unique, then we call function is differentiable at that point. So we have to check slope of a tangent, right? Say this is a function y is equal to fx. We have to find the slope of tangent at this point x is equal to a, that is we have to find the value of tan theta. So say let us make a function like this, the same function here, and we have say 2 points here and here. Okay. One point is say a minus h and another point is here is x is equal to a. So we can write this as fa and this as fa minus h, right, and this as h. Okay, so clearly here the slope of tangent is slope of this line, I mean green line, is m is equal to y upon x, delta y upon delta x, which is equal to f a minus h upon h, right? Or say if we have a function, again let us draw the function again. Say this is a function. This is a function, and at point, say let me take this point and this point as a now and this point as a plus h. So we have a line passing through point a and a plus h. Again we can find the slope of this line. This is delta y, which is fa plus h minus fa, and this side is, this length is h. So we have slope of red line as fa plus h minus fa upon h. Okay. See, when h tends to 0 in both the cases, the line becomes tangent. When h tends to 0 in both cases, that is in here where we have taken green curve and we have taken red curve, that is red line. So when h tends to 0, in both cases, let us name this case as case 1 and this as case 2. So in both cases 1 and 2, the line becomes tangent at point A, right? And we have the slope of tangent as tangent at A. Slope of tangent, we can write it as limit h tends to 0 f a plus h minus f a upon h. This should also be equal to limit h tends to 0 f a minus h upon h, right? So this is called slope of a tangent, right, at point A. If both are equal, then we have a unique tangent, or if both are unequal, then we don't have a unique tangent. That is, the function is not differentiable at point x is equal to a. So this term is called right hand derivative. Right hand derivative, that is RHD, and this term is called left hand derivative, because we are finding the slope of tangent from left side, right, from left of A, and here in this case we are finding the slope of tangent from right of A. So we have right hand derivative and we have left hand derivative, LHD. So for a function to be differentiable, at x is equal to a, its left hand derivative must be equal to right hand derivative, right? And if this is the case, then we call function is differentiable at point A and its derivative is defined as f dash a, as the expression of whatever we have written above. Limit h tends to 0 f a plus h minus f a upon h, or equally good as limit h tends to 0 f a minus f a minus h upon h. Generally, this is the familiar equation used in most of the books for finding derivative of function. But this is also equally good. So we can use any of the two equations to find the derivative of function if it is differentiable at point A, right? So now we have seen the condition for a function to be differentiable at point x is equal to a. Let us now see the formula of some of the derivative of a function, smooth function, which is smooth, right? So its derivative is defined as point x is equal to all points x is equal to a, where a is in its domain, right? So for a function, say let us see if fx is equal to x to the power n, then we write f dash x as x to the power n minus 1. Okay. So let us make a table, fx here and f dash x there. Okay. So for x to the power n x to the power n minus 1. For sin x, the differentiation is, derivative is cos x. For cos x is minus sin x. For tan x is sec square x. For sec x is tan x sec x. Okay. For cosec x it is minus cot x, cosec x, and for cot x it is minus cot square x. For e to the power x, the derivative is e to the power x itself. For log x base e, the derivative is 1 upon x. Okay. So we have a derivative of function which is defined like this. This all formula can be derived using this basic equation, right? Which is we have seen. We can use any of these two formulas, that is for f dash a. Okay. This is also known as differentiation using first principle. You can write it as also first principle. Okay. Now we have two important theorems. One is Sandwich theorem. Okay. According to this theorem, if we have a function fx and we have a function gx, okay, and we have a function hx, such that hx is less than equal to fx is less than equal to gx, okay, then if limit x tends to a hx is equal to limit x tends to a dx is equal to say L, then we have limit x tends to a fx is also equal to L. Okay. So this theorem is known as Sandwich theorem. Let us have an example. Evaluate limit n tends to infinity greatest integer of x plus greatest integer of 2x plus greatest integer of 3x plus dot 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 greatest integer of nx upon n square. So how to evaluate this limit? Okay, so we have a relation. Greatest integer of x is always less than equal to x, right? And it is always greater than x minus 1, obviously. Similarly, we can write greatest integer of 2x is always less than equal to 2x and always greater than equal to 2x minus 1. Similarly, we have this relation. Suppose we add all these three. So what we get? We get greatest integer of x plus greatest integer of 2x plus greatest integer of 3x is always less than equal to x plus 2x plus 3x, and in this side x plus 2x plus 3x minus 3. Okay. So similarly, up to n, if we add, then we will be getting right from this up to 3 we have added. So in this side, left hand side, we have got x plus 2x plus 3x minus 3, and in right hand side we have got x plus 2x plus 3x. So similarly, in right hand side, in general we will be getting x plus 2x plus dot 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 nx, and in left hand side we will be getting x plus 2x plus 3x plus dot 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 nx minus n. So we can divide it by n square all sides. Now we have, if we use Sandwich theorem, so let us name fx as x plus greatest integer of x plus greatest integer of 2x plus dot 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 greatest integer of nx upon n square dx as x plus 2x plus dot 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 nx upon n square and hx as x plus 2x plus dot 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 nx minus n upon n square. Okay. Now clearly we have hx is less than equal to fx is less than equal to gx, right? And if we see the limit n tends to infinity, limit n tends to infinity, hx is equal to x plus 2x plus dot 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 nx upon n square minus 1 upon n, which is equal to x 1 plus 2 plus dot 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 plus n upon n square minus 1 upon n, which can be written as x into n plus 1 upon 2 n square minus 1 upon n. Further can be written as n and n can be cancelled. So we have x into n plus 1 upon 2n minus 1 upon n. Taking 1 upon n as common, we can write as x n plus 1 upon 2 minus 1, which can be written as x n plus x minus 2 upon n, right? So if you see what is the value of limit n tends to infinity, x n plus x minus 2 upon 2n. So it can be equally written as limit 1 upon n tends to 0, right? And dividing it by n, we have x plus x upon x minus 2 upon n upon 2. So 1 upon n tends to 0, so we have this limit as equal to x upon 2. Similarly, we have limit gx extends to infinity as x 1 upon n upon 2. N tends to infinity. This is also x upon 2. So using Sandwich theorem, we can say that limit fx, which is our original function, n tends to infinity, is also equal to x upon 2, right? So the value of the limit is equal to x upon 2. Okay. We have one more theorem, which is not basically a theorem, it is called a rule. Lateral rule. In hospital, it is pronounced as lateral rule. So if we have limit x tends to a, fx upon dx, and fx upon gx is of the form means undeterminate form. We are talking about undeterminate form. Form is of the form 0 by 0 or infinity by infinity. Then we can write limit x tends to a fx upon gx equal to limit x tends to a f dash x upon g dash x equal to limit x tends to a, and if this is also the form of 0 by 0 and infinity by infinity this term, then further we can differentiate it, that is f double dash x upon g double dash x. Still we will not be getting this form, right? So this is L'Hospital's rule. This rule is very useful in evaluating the limit of a function. So this is all about the theory, basic theory of limit continuity and differentiability. Now we will be solving some problems. Okay. We have our first problem, limit x tends to 5, x minus 5 upon absolute value of x minus 5 or mod of x minus 5 equals to. So we can write it as, say, if x is greater than 5, then we can write limit x is equal to 5 plus, or we can write it as x minus 5 upon mod of x minus 5 is same as x minus 5, right? Because x is greater than 5. So we have x minus 5 as 1, right? But when x is less than 5, then mod of x minus 5 is not equal to x minus 5. It is equal to minus of x minus 5, right? So we have limit x tends to 5 minus x minus 5 upon minus of x minus 5, which is equal to minus 1, right? So the two limits are not equal. Okay. So the limit does not exist at x equal to 5. We say that limit x tends to 5 plus fx is not equal to limit x tends to 5 minus fx, right? So limit x tends to 5 fx does not exist, right, in option. So none of the options are correct. Option D, none of these is the right one. Okay. Now moving to the next question. We have fx is equal to sine of greatest integer of x upon greatest integer of x, when greatest integer of x is not equal to 0, and 0 when greatest integer of x equal to 0. Okay. Denote the greatest integer of x where bracket of x denotes the greatest integer less than or equal to x, then limit x tends to 0 fx is. Okay. So again here also we will be doing the same method. First, we will be seeing limit x tends to 0 plus fx, that is right hand limit. If x is just greater than 0, then greatest integer of x is 0 itself, right? So we have 0 by 0 form, so this limit is 1. Okay. Now, if limit x tends to 0 minus fx is limit x tends to 0 minus if x is just less than 0, we have greatest integer of x is minus 1, right? Suppose we have, say, minus 0.1. So what is its greatest integer? Its greatest integer is minus 1. Okay. So its value is sine minus 1 upon minus 1, which is not equal to 1. Again here also limit x tends to 0 plus fx is not equal to limit x tends to 0 minus fx. So this limit does not exist. Okay. So here also none of this is correct, right? Now moving to the third problem, we have limit sine pi by 3 minus x upon 2 cos x minus 1. So let us check first what is the form of this limit. So we have sine pi by 3 minus pi by 3 which is 0 and 2 cos pi by 3 minus 1 which is equal to 2 times half 1 minus 1 is equal to 0. So this is 0 by 0 form. So we can use L'Hopital's rule, right? So we can write limit x tends to pi by 3 sine pi by 3 minus x upon 2 cos x minus 1 as differentiating this above and below. We can write differentiation of sine pi by 3 minus x as minus of cos pi by 3 minus x. Okay, and 2 cos x, its differentiation is minus 2 sin x, right? And the differentiation of constant term, that is 1, is 0. So here we can write minus cos 0 upon minus 2 sin pi by 3. So obviously this minus minus get cancelled. We have cos 0 as 1 and sin pi by 3 as root 3 by 2. 2 times root 3 by 2 is root 3. Okay, so option B is the correct one. Moving to the next question, we have problem 4. The number of points at which the function fx is equal to 1 upon log mod x is discontinuous is. So we have to check where the function 1 upon log mod x is discontinuous. Let us see first the behavior of function y is equal to log x. Function y is equal to log x is something like this. This domain is from 0 to plus infinity and range is from minus infinity to plus infinity. The function is 0 at x is equal to 1, right? So at x is equal to 1, log x is equal to 0. That means at x is equal to 0, 1 upon log x is infinity. So it is discontinuous at x is equal to 1. As well as, since this is mod x here in place of x, at x is equal to 1 as well as at x is equal to minus 1, the function is discontinuous. Okay, and at x is equal to 0, it is infinity, right? Log mod x is infinity. So we have 1 upon log mod x is 0 at x is equal to 0, right? So the number of points where the function is discontinuous is 2 points, that is at x is equal to 1 and at x is equal to minus 1. Because at x is equal to 1, 1 upon log x is infinity, as well as at x is equal to minus 1, 1 upon log x, mod log x is infinity. So at both these points, that is at x is equal to minus 1 and at x is equal to 1, the function is discontinuous. So we have option B as correct option. Now moving to the next problem. The set of all points where fx is equal to x mod x is differentiable is. So we have to find the set of points where the function fx is equal to x mod x is differentiable. So we can write this function x mod x as x square when x is greater than 0 and minus x square when x is less than 0. So if we try to draw the graph of a function, then we see for x greater than 0, this curve is valid, and for x less than 0, this curve is valid. Okay, so the overall graph of function is something like this, right? So let us check. So this is our point of concern. So let us check whether the function is differentiable at this point or not. So let us find right hand derivative. So right hand derivative is 2x which is equal to 2 times 0, 0, and left hand derivative is minus 2x, which is again equal to 2 times 0, which is 0. So at x is equal to 0, the function is differentiable because left hand derivative is equal to right hand derivative, right? So it is differentiable at all points from minus infinity to infinity. So option A is correct. Okay. Moving to the next question. Problem 6. In order that the function f(x) is equal to x plus 1 to the power cot x is continuous at x is equal to 0. f0 must be defined as. Okay. So let us find what is the value of f0 is coming. f0 is 1 plus 0 to the power cot 0. Cot 0 is cos 0 upon sin 0, which is infinity, right? Cot 0 you can write as cos 0 upon sin 0, which is equal to 1 upon 0, which is infinity. So this is basically the form 1 to the power infinity. So undeterminate, right? So we have to set it in the form 1 plus x to the power 1 upon x, because we know limit x tends to 0, 1 plus x to the power 1 upon x is equal to e, right? Using this we can write f(x) is equal to 1 plus x to the power 1 upon x into x times cot x, right? And hence we can write limit x tends to 0, f(x) is equal to limit x tends to 0, 1 plus x to the power 1 plus 1 upon x into x cot x. Further, we can write it as limit x tends to 0, we can write it as, this can be written as e, so we can write it as e to the power limit x tends to 0, x cot x, right? So we have to evaluate the limit x cot x. Cot x we can write as x, cot x we can write as cos x upon sin x. Now limit x tends to 0, x upon sin x can be written as 1 and cos x is also written as 1. So we have this one. So this can be written as simply e. Now at x is equal to 0, the limit of f(x) is coming as e, and when we are talking at point exactly at x is equal to 0, the limit is the function value cannot be defined because it is undeterminate. It is tending to e at 1 plus and 1 minus, right? So at x is equal to 0, if we define the function, the value of function as e, then we have the relation f0 plus is equal to f0 minus is equal to f0 is equal to e. Then we can say that at x is equal to 0, the function is continuous. So for this we have to define the value of function at x is equal to 0 as e, right? So option B is correct here. Moving to the next question, we have f(x) is equal to x bracket root x minus root of x plus 1. Then at x is equal to 0, right hand derivative exists but left hand derivative does not exist. So basically we have to check the differentiability of a function f(x) at point x is equal to 0. So we have f(x) as x root x minus root x plus 1, right? Now say if we are calculating right hand derivative, so we define right hand derivative as limit h tends to 0, f 0 plus h, because here 0, this is 0 because we are finding derivative at x is equal to 0, f 0 plus h minus f h upon h, right? So what is the value of f 0 plus h here? So we can write f 0 plus h as 0 plus h times 0 plus h minus root under 0 plus h plus 1, right, upon let me correct it. So we can write f0 plus h as 0 plus h root under 0 plus h minus root under 0 plus h plus 1, which is equal to h root h minus root h plus 1, right, and f h is h root h minus root h plus 1, right, because this is what the function is, x minus root x plus 1. Okay. So here the value of f0 plus h minus fh, both values are same, right? So we have this value as 0. So its right hand derivative is equal to infinity plus positive infinity, because h is tending to plus 0, right? So we have right hand derivative tending to plus infinity, and if we are calculating left hand derivative, so let us calculate left hand derivative. Left hand derivative, it is defined as limit h tends to 0 minus, okay, I mean h tends to 0. Here also this is h tends to positive 0, but instead of f0 plus h we are writing fh minus f0 minus h upon h. So we have to calculate f0 minus h, which is equal to 0 minus h root under 0 minus h minus root under 0 minus h plus 1 by r. So this is equal to minus h times root under minus h plus minus h plus 1. So basically 0 minus h is not defined. Why? Because we have this term root under minus h, which is negative, because h is positive. So this is not defined. So LHD is actually not defined. So at x is equal to 0, the function is not differentiable. So RHD exists, but LHD does not exist. LHD exists, but RHD does not exist. This option is incorrect. Why? Because LHD is not defined, right? So LHD does not exist. Similarly, fx cannot be differentiable, because LHD, for fx to be differentiable, LHD is equal to RHD, right? And since RHD is infinity, which is, we cannot say what number it is, so RHD also does not exist, right, at x is equal to 0. So we have option left, none of this. Okay. So now moving to the next question. We have limit x into 0, 1 plus ax plus bx square to the power 2 upon x is equal to e cube. Then a and b are equal to, we have to find the value of a and b, for which this limit is equal to e cube. Okay, so let us first see what is the form of this limit. So we have fx is equal to 1 plus ax plus bx square to the power 2 upon x. Okay, so f0 is 1 to the power infinity, right? So this is also the form 1 to the power infinity, which is undeterminate. So now again we are going to use the formula limit x tends to 0, 1 plus x to the power 1 upon x is equal to e, right? So we can write fx as 1 plus ax plus bx square, okay, to the power 1 upon ax plus bx square. into 2 times x into ax plus bx square, right? So this will be equal to e as x tends to 0, because this is totally based on this formula, right? And we have the limit 2 into ax plus bx square upon x is equal to 3, because it's limited. In question it is given that this limit is equal to e cube. So this must be, that is, limit 2 ax plus bx square upon x as x tends to 0 must be 3, or we can write as 2a plus 2b x, right, as x tends to 0 must be 3. So we have a as 3 by 2, and if b is equal to, say b is equal to b, here it is given b not equal to 1, and there is option b is equal to 4. So b can be any value, right? So b, because here x is tending to 0, so we have as x tends to 0, this b will be vanished. So 2a is equal to 3. So we are getting the value a is equal to 3 by 2 from here. We are not getting any value of b. So b can be any value, right? So here a is equal to 3 by 2 is in options b and c. So we have the options b and c, both are correct, right? Now moving to the next question. If fx is equal to greatest integer of x sin pi x, then fx is continuous in -1 to 1, differentiable at x is equal to -1, differentiable at since now we have to check the differentiability and continuity, okay, of the function. Fx is equal to greatest integer of x sin pi x, right? Now let us see the nature of this function sin pi x. Let us see the nature of function sin pi x. So the function sin pi x will be something like this, where its period is 2 pi upon pi, that is 2. So this value is 1, this value is 2, this value is 3, and obviously this value is, the sin pi x lies between 1 and -1. Okay. So say if x lies between 0 to 1, okay, then sin pi x also lies between 0 to 1. Why? Because in 0 to 1 it is between 0 to 1, right? From the graph it is clearly visible. So sin pi x also lies between 0 to 1. So x sin pi x also lies between 0 to 1. So when x is between 0 to 1, then we have fx is equal to 0. At x is equal to 1, we have sin pi, the value of sin pi is 0, and the value of x is 1. So we can actually close the interval, that is from 0 to 1. Fx is 0. And for x is equal to, from x is equal to -1 to 0, if we check, then we see that if x is negative, then sin pi x from -1 to 0, from -1 to 0, it is also negative, right? Sin pi x is also negative. So both will result to positive. So here also greatest integer of x sin pi x, when x is from -1 to 0, is again 0, right? So fx is 0 from, for x belonging to -1 to 1, right? Close interval. Okay. So we have the function is continuous, is clearly continuous in -1 to 1. So option A is correct here. Now checking the differentiability at x is equal to 1 and -1. So if we see the continuity of function, first let us check the continuity of function at x is equal to 1 and -1. So if we see if x is greater than 1, say x is greater than 1, let us take x between 1 and 2. Okay, so sin pi x in that case will be negative and x is positive. Say let us take 1.5. So 1.5 at 0.5 sin pi x is negative. So it is -1, right? So we have greater than 0 -1.5, which is equal to -2. Okay. So 1.5 times -1 greater than -1.5, which is equal to -2. So at x is equal to x greater than 1. If we take x just greater than 1, let us take x just greater than 1. Then its value will be, say x is 1, something greater than 1, and this sin pi x is negative, -1. So it is something greater than point minus something. So its value will be, its greatest integer will be something negative which is just less than 0. I mean just less than 0, and it is negative, something 0 point something. Okay, which is whose greatest integer is -1. So the function is not continuous at 1, right? Similarly, if we see the continuity of function at x is equal to -1, say if x is just less than -1, that is x is equal to -1 minus. Okay, so we have the function. This function x sin x is positive, whereas x is negative. So again we will be getting negative value. So we are not getting the value 0. At x is equal to -1, just before and just after, we are not getting the value same value, right? Because at x is equal to 1 minus, that is, if x is just less than 1, we have fx is equal to 0. And for x is just greater than 1, we have fx is equal to -1. Similarly, for fx to be 0, at x is equal to -1, just greater than -1, we have fx is equal to 0. And for x just less than -1, we have fx is equal to again -1. So the function is not continuous at x is equal to either x is equal to 1 or x is equal to -1. So since the function is not continuous, there is no point that the function is going to be differentiable, because if a function is not continuous, say this is a function which is not continuous, then at this point we cannot talk about its differentiability. That is, it is not differentiable at this point. Okay, so to be differentiable, first the function has to be continuous at that given point. So these two options cannot be correct. So option 1 is only correct. Now moving to the next question. The function fx is equal to mod of x cube is differentiable everywhere. Again we have to check the continuity and differentiability of the function. So the best method is the graphical method. We have the function y is equal to x, y is equal to x cube like this. Okay. So mod of x cube can be something like this. Okay. So let us check now here the point of candidate. The candidate is this point, that is x is equal to 0, because at this point we are changing the curve. So we have to check whether it is differentiable or continuous at point x is equal to 0 or not. So from here from the graph it is clearly visible that the function is continuous. Now we have to check the differentiability of the function. So for fx is equal to mod of x cube, if we see x is greater than 0, then fx can be written as simply x cube. And if x is less than 0, then fx can be written as minus x cube, right? So in both cases, if we evaluate f as 0, we will be getting 0, right? So that means RHD is equal to LHD. Left hand limit is equal to right hand. Right hand derivative is equal to left hand derivative. So it is also differentiable at x is equal to 0. So we have option A as correct, that is differentiable everywhere. Okay. So these are the problems of limit, continuity and differentiability. Now next we are going to discuss derivative and applications. Okay. Thank you.